Okay. Hello everyone. My name is Papia and the course name under which I am doing the PhD, the course name is Classical Mechanics of a Single Particle and the course instructor is Professor Supratik Banerjee. So today we will talk about week 12 assignment 12 question paper with the detailed, like it was the previous year question paper with the detailed analysis. So there will be again as usual 20 questions and there will be some explanation of these questions. But I just want to make sure here that this is the last class of our Classical Mechanics of a Single Particle 2025 course. So all the very best for your exam, and we will just simply wrap up this class a little bit within 1.5 hours or something like that, so that you can have plenty of time for yourself to prepare for your exam, final exam very well. So here basically we will talk a very simple questions, like obviously there will be some little bit tricky questions, but as sir was mentioned in his lecture in the week 12, I can also tell that these questions in the week 12 or assignment 12 questions are little bit not that much relevant for our, it is not directly related to our classical mechanics of a single particle core subject, what we are going to, what we have already learned up to this, but it is little bit advanced one. Okay, so week 12 is little bit advanced, and obviously there is some conclusion regarding the importance of the classical mechanics of a single particle, and all these things were discussed by SAT. So the thing is that I just want to make sure here that maybe it might be possible that none of the questions or very few number of questions are coming from this week, like week 12 or assignment 12 in final exam, because as again I'm telling that this is a advanced level topic. So even not only I am talking, sir was also pointed out these things in his lecture. But obviously for an advanced level of understanding or advanced level of knowledge, I have to know, and we have to know more about this thing that Lorentz equations. Then there was like spiral contour, and then limit cycles and all these things. But yeah, again I can tell that this is not for this topic, this exam, classical mechanics of a single particle NPTEL exam. It is a little bit advanced topic, but yeah, we will just talk a little bit about these questions, and we will see that what will be the answer for these questions and how we can address these questions. Okay. So the first question is, Lorentz equations cannot describe the motion of a single particle because. Okay. So Lorentz equations cannot describe the motion of a classical particle. Why? There are four options. All parameters are positive. The evolution equations are nonlinear. The phase space dimension is even. The system has a fixed point. Okay, so for answering this question, not only for this question, for all of the questions in this today's class, I just want to make a little bit note type thing, so that all the things will be very clear for all of you. And also, if whoever has not joined the class of today's class, that will be obviously recorded, and I will upload that one in YouTube, so that you can you can see these things in a later as well. And even in this I can also tell that this PPT will be available later as well in Google Drive, so you can just directly go through there, and you can just download from there these PPTs, and this PPT will give you all the information about these questions as well as their answers. Okay, so coming to the first question, as first question told us, Lorentz equations cannot describe the motion of a single classical particle, but why? Okay, so this is the question. So let me first write here the Lorentz equation, why it is not giving the equation for the single particle, sorry, for the classical particle, right? Yeah. So I'm just writing here the Lorentz equation describes a system with three coupled nonlinear first order equations, and specifically it is in 3D. So this is the main line for this question. The Lorentz equation basically describes a system with three coupled nonlinear first order equations, and in 3D. I am talking about 3D, right? But a classical particle has an even dimensional phase space. How even dimensional phase space is coming? Let's say the coordinate is there. Let's say position and their corresponding momentum, right? So whenever I will talk about, let's say 1D, but that one position, but obviously phase space will give me 2D, one position, one momentum, right? So I can see that like for the classical particle it has a even dimensional phase space. So even dimensional phase space means position, if position is there, then corresponding momentum will also be there. So the for the phase space in classical mechanics, the dimension is like 2D, 4D, 6D, something like that. Okay. So obviously now we can understand that since the Lorentz equation has odd dimension and classical particle phase space needs even dimension. So that's why Lorentz equations cannot represent the motion of a classical particle. Okay. So what is the question told and what is the explanation for this? Lorentz equations cannot describe the motion of a single particle because the phase space dimension is even, right? And for Lorentz equations it is basically taking the 3D, 6D or something like that. So obviously it is not going to explain the classical mechanics, the classical particles motion. Okay. Now I can go for the next question. The van der Pol oscillator cannot describe a Hamiltonian system because the van der Pol oscillator cannot describe a Hamiltonian system. Okay, very good. But what is the reason between that? I mean, what is the reason behind that? So, for this question, I just want to write here the van der Pol oscillator contains a damping term that basically depends on x square. So what is the equation for van der Pol oscillator? The equation for van der Pol oscillator is x double dot minus mu into 1 minus x square x dot plus x equals to 0. Now in this equation you can see that 1 minus x mu into 1 minus x square x dot is there. So this is basically giving me this non-linear damping breaks the energy conservation. As it breaks the energy conservation, the system is non-Hamiltonian. So it cannot describe a Hamiltonian system because obviously we can see that it involves a nonlinear damping. And how I can confirm that one? I can confirm that from this the van der Pol oscillator equation, that which is x double dot minus mu into 1 minus x square x dot plus x equals to 0. So here you can see that there is a x square term in the damping term. So there is a x square term. So x square term is basically giving me the non-linearity, which again told me that the energy is not conserved in this system, and the energy conservation it is breaking. So that means the system is non-Hamiltonian. So the actual answer for this question is 2. It involves nonlinear damping. That's why van der Pol oscillator cannot describe a Hamiltonian system. Okay, now coming to the next question. Which of the following statements is true about a limit cycle? Okay, so the options are: it can exist only in linear systems, it requires a Hamiltonian formulation, a limit cycle is a distinct closed trajectory in phase space, a limit cycle only appears in 1D systems. Okay. So the question is about the limit cycle. So first of all, I just want to mention here what is limit cycle. Yeah, so here I just want to mention what is limit cycle, because it basically consists 4 options. It can exist only in linear systems. It requires a Hamiltonian formulation. It requires a limit cycle is a distinct closed trajectory in phase space. A limit cycle only appears in 1D systems. So what is limit cycle, that we need to understand. So a limit cycle is an isolated. So we just mentioned these terms very carefully, that it is an isolated periodic orbit in phase space. Now so basically nearby trajectories approaches or move away from it. How? It is depending on its stability, right? So basically limit cycle is an isolated periodic orbit in phase space. Now nearby trajectories throughout, I mean, on the limit cycle, nearby trajectory is going approaches or move away from it, and how it is going to depend on its stability. So basically, stability means you can understand the stable spiral, unstable spiral. This type of conditions is coming here. But so that means it is a non-linear phenomena. Obviously, for limit cycle, I can tell here that right, it is a non-linear phenomena, and so that means what? That linear systems cannot have the limit cycles, right? So from the option you can see that which of the following statements is true about a limit cycle. It can exist only in linear system. No, at the very first it is not correct, because I told that the limit cycle is only for the nonlinear systems. It requires a Hamiltonian formulation. No, that is also not correct, because for that nonlinear systems we are not having the Hamiltonian formulation, as I already mentioned in the previous question. So now coming to the third option, a limit cycle is a distinct closed trajectory in phase space. Yes, that is correct. It is a distinct closed trajectory in phase space, and it is coming through the definition itself. And a limit cycle only appears in 1D system. No, that is also not correct. It is not needed to have a 1D system. So, the final answer for this question, which of the following statements is true about a limit cycle, is that a limit cycle is a distinct closed trajectory in phase space. Okay. Now, maybe we can have the next question. Yeah. So, the next question is again on the limit cycle, and obviously it is very similar to the first one, I mean the previous one. So, yeah. So, the limit cycle is a nonlinear dynamical system, is best described as a closed trajectory in phase space that is stable under small perturbations, a periodic orbit that exists only in linear systems, a trajectory that always shrinks to a fixed point, a path that repeats only in conservative systems. Okay, so from these four options, I can directly see, I mean, by seeing, I can directly cut two options. Okay, what is these two options? One option is the periodic orbit that exists only in linear system. That is not correct, because as we already mentioned that limit cycle is only for the nonlinear systems. And also this fourth option, a path that repeats only in conservative systems. That is also not correct, because the limit cycle is again applicable in nonlinear systems, and in nonlinear systems you can understand that the conservation system, like non-Hamiltonian will be there, and for non-Hamiltonian means it is it does not conserve energy. So like conservative system is not there. Okay, so by seeing these four options, I can directly cut one option. Two options. Now coming to the other two options. Then which one will be the correct one? Just a minute, there is a So for the explanation of this question, I just want to write here something. Let me write here. It is. Oh. So basically, okay. So in that question, a limit cycle in nonlinear dynamical system is described as. So the first question is about the stable, right? Stable limit cycle. So we need to know that what is stable limit cycle, and in the second one, the third one is trajectory that always shrinks to a fixed point. Okay. So now coming to the first option as stable one. So stable limit cycle is what? So a stable, limit cycle is a closed orbit such that nearby trajectories spiral towards it over time. Yeah, I'll explain what does this means. So basically, and also this represents a self-sustained oscillation typically in nonlinear system, as I already mentioned. Let's say let's say Van der pole oscillator. Yeah, that is one of the option, like one of the example of this self-sustained oscillation. Even in the stable limit cycle example. So, what is stable limit cycle? The stable limit cycle is a closed orbit that nearby trajectories spiral towards it over time. So, in that stable limit cycle, the spiral trajectories are coming inside, like it is coming inside of this stable limit cycle. It is coming towards the limit cycle over time. So this represents a self-sustained oscillation typically in nonlinear system like Van der Pol oscillator. Now coming to the options here talking. So a limit cycle in a linear dynamical system is best described as a closed trajectory in phase space that is stable under small perturbations. Yes, it is. Why? Because if I have a small perturbation, then also over time a closed trajectory in phase space is going to surround around that limit cycle. So the first option is correct. A trajectory that always shrinks to a fixed point. No, it cannot be a it is not a shrinks to a fixed point, but basically it will do a closed orbit that nearby trajectories spiral towards it over time. So there is a subtle differences between 1 and 3 options, but the best representation will be obviously a closed trajectory in phase space that is stable under small perturbations. Okay, now coming to the fifth one. In 2D phase space, if the coefficient matrix has distinct eigenvalues, the eigenvectors will be. Okay, fine. So first of all, what is coefficient matrix? So the coefficient matrix, I can write it as Ka. Obviously, in the next questions, we will basically define it as A. So how it is going to form? Like let's say x dot, y dot, A, x, y, and A will be a 2x2 matrix. So in 2D, obviously. So in 2D, A is a 2x2 matrix, right? Okay. So this is the coefficient matrix. In 2D phase space, if the coefficient matrix has distinct eigenvalues, the eigenvectors will be what? Okay. So obviously I can say that if A has distinct eigenvalues, its eigenvectors correspond to different directions in phase space and are always linearly independent. Okay, so if our A has two distinct eigenvalues, so let's say A have A, B, C, D, something like that, and the eigenvalues are lambda 1 and lambda 2, these are distinct, then there will be a linearly independent eigenvectors. So the eigenvectors will be linearly independent. Okay. So this basically conclude me for the 5 questions. So now coming to the 6th one. Yeah. If, okay, again I just want to write here this one. This one. This Jacobian matrix is nothing but coefficient matrix, what I told here, which is basically mentioned that A. So how it is coming? X dot y dot x y and A. If the Jacobian matrix of a 2D system has complex conjugate eigenvalues with negative real parts, the fixed point is, okay, let me just, yes. So if A has complex conjugate eigenvalues with negative real part, then trajectories spiral inward. Toward the fixed point, which basically told us stable spiral of focus. So let's say as an example I can have lambda 1, lambda 2. Lambda is like minus 1 by 2 plus minus root 3 I by 2. So here you can see our lambda 1 is minus half plus root 3 I by 2. Lambda 2 is minus half minus root 3 I by 2. So among these two, minus half is there as a real part with the negative sign. Here also negative sign. So these type of eigenvalues will basically ended with the stable spiral point. So now coming to the option here, it is stable spiral. Okay, so the full fixed point is stable spiral. Okay. Now coming to question number 7. A chaotic motion is what? Necessarily periodic, aperiodic, only possible in 1D, always deterministic with periodic solutions. Okay. A chaotic motion by name itself I can say is a aperiodic. That means non-repeating and also sensitive to initial conditions. Though it is deterministic, but however therefore chaotic motion is not periodic or random. It is aperiodic. Actually, the chaotic motion means it is aperiodic. That means it is not repeating after a specific time interval to a same position, but it is sensitive to initial conditions, though also it is deterministic. So deterministic means obviously we can't tell that it is a random number generator or randomness is there, like truly random is there. Obviously that is not correct, but it is a aperiodic because it is not repeating. So necessarily periodic, that is also not correct. Aperiodic is correct, only possible in 1D, always deterministic with periodic solutions, that is not correct. So aperiodic is correct. Okay, now coming to the 8th question. A system that exhibits sensitive dependence on initial conditions but evolves deterministically is said to be. Yeah, so similar question was there in the previous question. So again, I just want to write here a system that is deterministic but sensitive to the initial conditions is said to be chaotic. Small changes in initial values lead to vastly different trajectories, though no randomness is involved. So, chaotic motion is like that the system will be aperiodic. There will be not the repeating same point repetition over a certain period of time, but it will be totally deterministic and sensitive to the initial conditions. If the small change in the initial condition is there, then there will be a vastly different trajectories, although it is not a randomness. So a system that exhibits sensitive dependence on initial conditions but evolves deterministically is to be said to be obviously chaotic. Okay. Now coming here to question number 9. For the system x dot equals to y dot equals to x minus y, the fixed point at origin is. Yeah. So for this case, like what is the nature of the fixed point? We need to calculate the value of coefficient matrix. Like the eigenvalues of the coefficient matrix. Then how to calculate the coefficient matrix and the eigenvalues of coefficient matrix? Okay. So coefficient matrix is coming out as like this. Now, what are the expressions given? The expressions are x dot equals to y dot equals to x minus y. Now, if I want to write here like that, then what will be the answer? This will be like 0, 1, 1 minus 1. Okay. Now, we need to check the eigenvalues of this. So, that means I can write here a is 0, 1, 1 minus 1. So, have to have the eigenvalues, I can need to have the characteristics equation. So, this is like minus lambda 1, 1 minus 1 minus lambda equals to 0. So, this will give me the answer as minus lambda minus 1 minus lambda minus 1 equals to 0. This is like lambda into 1 plus lambda minus 1 equals to 0, which told us that lambda plus lambda square minus 1 equals to 0, lambda square plus lambda minus 1 equals to 0. So lambda is minus 1 plus minus root over b square minus 4 ac. This will be plus by 2. So minus 1 by 2 plus minus root 5 by 2. Now you can see that our lambda is minus 1 by 2 plus minus root 5 by 2. So lambda 1 is minus half plus root 5 by 2. Lambda 2 is minus half minus root 5 by 2. So among these lambda 1, lambda 2, one is positive, another one is negative. So this will give me unstable spiral or saddle type instable plating. So you can understand from this is unstable spiral, which is the option number 3. So how we can conclude that this is an unstable spiral? So unstable spiral is coming because one is positive, another one is negative of lambda 1 and lambda 2. And saddle type instabilities are there. Saddle is there, but saddle type instabilities are there. Okay. Okay. Now coming to 10th question. For a system, x dot equals to y, y dot equals to minus x minus y. The origin represents stable spiral, unstable spiral, saddle point, center. Okay. So again, for this case, we just need to calculate the coefficient matrix, and then there will be the eigenvalues. Yeah. So x dot equals to y, y dot equals to minus x minus y. Sorry. So x dot y dot, this is 0, 1, minus 1, minus 1. Okay. So our A will be 0, 1, minus 1, minus 1. So the characteristics equation will be this. So this is like minus plus 1. So it will be lambda plus lambda square plus 1 equals to 0. So sorry. So lambda is minus b plus minus root over b square minus 4ac divided by 2. So minus plus minus minus 3 by 2. So I can write it like 3 by 2. So here we can see that lambda 1 is minus half plus root 3 by 2. Lambda 2 is minus half minus root 3 by 2. So here I can see that lambda 1 and lambda 2 are complex conjugate eigenvalues with negative real part. So as we already mentioned, this type of things are basically leads to us as stable spiral. So stable spiral means I can also write it as a decaying oscillation. So stable spiral, how? Because you can understand in this not here. No. Where? Yeah, it is stable spiral because you can see that if the real part is negative and both are complex in nature, obviously complex means complex conjugate should be there. So that will be stable spiral. So here also you can see that this is giving me the stable spiral. Yes. So as x dot equals to y, y dot equals to minus x minus y is giving the lambda 1 and lambda 2 as complex as well with negative real part. Okay. Now coming to question number 11. For the system x dot equals to x, y dot equals to minus x, which of the following is true? Yeah, this is very simple question, right? Okay. Trace of a and determinant of a, which one is correct? X dot equals to x, y dot equals to minus x. X dot equals to x, y dot equals to minus x. So quickly I can write here x dot equals to x, that means 1 0 minus 1 0. Yes. So our a is 1 0 minus 1 0. Now the trace of a is 1 plus 0, which is 1. Now coming to determinant of a, which is 0 minus 0, which is 0. So we can say that trace of a is 1, determinant of a is 0, right? So trace of a is 1, determinant of a is 0. That is correct. Any other option is not going to correct. Yeah. Okay, now coming to the next question. Consider x dot equals to y, y dot equals to minus x, then. Okay, this is very similar to the the previous question. So let us do that one very quickly. X dot equals to y. Okay. Y dot equals to minus x. So x dot y dot 0 1 minus 1 0. So a will be 0 1 minus 1 0, and the trace of a is 0 plus 0, which is 0. Coming to determinant of a, 0 1 minus 1 0, so it is like 0 minus of minus 1, which is plus 1. So the trace of a is 0. Determinant of a is 1. Right? So this is the first one is the correct option. Okay. Now coming to the third question, 13th question. For x dot equals to x minus y dot equals to x plus y, the eigenvalues of a are. Okay. So for this case, they are asking that what will be the eigenvalue for a. So let me write here x dot equals to what? Y dot equals to x plus y. So simply x dot y dot xy, it is 1 minus 1 1 1, right? So I can have my a coefficient matrix 1 minus 1 1 1. Now coming to the eigenvalues. 1 minus lambda minus 1 1 1 minus lambda, that will be 0. So 1 minus lambda plus 1 equals to 0. So it is like 1 minus lambda whole square plus 1 equals to 0. So 1 minus 2 lambda plus lambda square plus 1 equals to 0. Lambda square minus 2 lambda plus 2 equals to 0. So we can have the lambda as minus b plus minus root over b square minus 4 into 2. Yes. So it is 1 plus minus root over minus 4 by 2. So it is 1 plus minus I. Yes. So our eigenvalues for the equation x dot equals to x minus y dot equals to x plus y are 1 minus I, 1 plus I. So the correct answer is 1. So for that, what we have done, we just calculated the coefficient matrix A by putting these two equations, x dot equals to x minus y dot equals to x plus y. Now we calculated the eigenvalues of A. So we got the coefficient matrix as 1, minus 1, 1, 1. Then we calculated the eigenvalues for corresponding these things. Then it is coming out like 1 plus minus I. So lambda 1 is 1 plus I and lambda 2 is 1 minus I. That's it. Now coming to the 14th question. For x dot equals to y dot equals to minus x plus y. eigenvalues of the system matrix are. Okay, this is very similar to the previous question. So x dot equals to y. Let me write here x dot. Y dot equals to minus x plus y, right? Plus y, yes. So x dot y dot will give me. So this is 0, 1, minus 1, 1. Now our A is 0, 1, minus 1, 1. Now coming to the eigenvalues. So for eigenvalues it is minus lambda 1, minus 1, 1 minus lambda equals to 0. So it will come as like minus lambda 1 minus lambda then plus 1 equals to 0. So it is coming lambda plus. Okay, so the A was minus lambda, like minus, sorry, A was 0, 1, minus 1, 1. So the eigenvalues corresponding to that A will be like the determinant of that minus lambda 1, minus 1, 1 minus lambda equals to 0. Now if I just calculate this one, then it will come as minus lambda, okay, yes, so it will be lambda plus 1 equals to 0, so it is minus lambda plus lambda square plus 1 equals to 0, which is giving me lambda square minus lambda plus 1 equals to 0. Then lambda is minus 1 plus minus root over b square minus 4ac divided by 2. So it is like 1 plus minus root 3I by 2. Okay. So our lambda 1 is 1 plus root 3I by 2. Lambda 2 is 1 minus root 3I by 2. So yes, now I can have this first option. So for x dot equals to y, y dot equals to minus x plus y, the eigenvalues of the system matrix are 1 plus I root 3 by 2, 1 minus I root 3 by 2. Okay. Now coming question number 15. For x dot equals to x minus y, y dot equals to x plus y, in polar coordinates, the equation is. Okay, this is a very tricky question, not that much tricky, but yeah, still. X dot equals to x minus y, y dot equals to x plus y. Yeah. X dot equals to x minus y, y dot is x plus y. First of all, polar coordinate means r and theta will be there, right? So in that polar coordinate, as r and theta is there, so our x should be written as r cos theta, y is r sin theta, that we all know. Okay. Now our expression is this one. That means I have to convert x dot y dot in terms of r dot theta dot, x and y in terms of r and theta. X and y I have the values, but I don't have the x dot and y dot value. So we will just calculate that one right now. This is x equals to r cos theta. So x dot will be r dot cos theta plus r okay, let me write here. So this will be minus r sin theta theta dot. Now y equals to r sin theta. So r y dot is r dot sin theta plus r cos theta theta dot. Okay. So x dot was x minus y. So I can write here r dot cos theta minus r sin theta theta dot equals to r cos theta minus r sin theta. And y dot equals to x plus y. This will give me r dot sin theta plus r cos theta theta dot equals to r cos theta plus r sin theta. Let me put here equation number 1. This is equation number 2. So from 1 and 2 we need to calculate r dot and theta dot. How we will calculate that one? Okay, simply we can do equation 1 into cos theta plus 2 into sin theta. So what it will come? It will come as r dot cos square theta plus sin square theta plus theta dot sin theta cos theta minus sin theta cos theta equals to r cos square theta plus sin square theta minus sin theta cos theta plus sin theta cos theta. You can do that one by yourself as well. You can understand that one very clearly. Now this is 1 plus theta dot into 0 equals to r into 1 minus 0. So that means r dot equals to r. I am getting. Okay, very good. Now coming to theta dot. If r dot equals to 1, then simply I can come here from equation 1. R dot cos theta minus r sin theta theta dot equals to r cos theta minus r sin theta. R dot equals to r. So I am just representing r dot as r cos theta minus r sin theta theta dot equals to r cos theta minus r sin theta. Now we can see here that okay, r cos theta minus r cos theta plus r sin theta equals to r sin theta theta dot. I just did the side change. So you can see r cos theta is cancelled out. So r sin theta equals to r sin theta theta dot. So obviously from there I can conclude theta dot equals to 1. So r dot equals to r, theta dot equals to 1. This is my final expression. So coming to the option here, yes, r dot equals to r and theta dot equals to 1. So for this case, what I did, I calculated x dot equals to x minus y and y dot equals to x plus y. X plus y was given, and in polar coordinates x equals to r cos theta, y equals to r sin theta. So I just put the x dot and y dot in terms of r dot and theta dot. So this is coming as x dot equals to r dot cos theta minus r sin theta theta dot, y dot equals to r dot sin theta plus r cos theta theta dot. Then we just put these things in our equation number 1 and 2. Then we just multiply it 1 and 2, these things, 1 into cos theta plus 2 into sin theta. So from there we are getting r dot equals to r. From this value we are just putting r dot equals to r and we are getting theta dot equals to 1. So r dot equals to r, theta dot equals to 1. Okay. Now coming to question number 16. In polar coordinates, if a system is described by r dot equals to 0, theta dot equals to omega, then the motion is, that is a good question. Good question in that sense I will tell, because I will just explain this. R dot equals to 0, theta dot equals to 1. That means r is constant. That's why r dot is 0, right? And theta dot is omega. So what does this means? If r dot equals to 0, theta dot equals to omega, the radius of the motion of the particle stays constant always. As I told you that r is constant, that's why r dot is 0, right? Okay, from this I can tell. And theta dot equals to omega, this basically told me that angle increases uniformly, right? So this basically represents uniform circular. Why circular? Because r dot equals to 0, r is constant. Why uniform? Because theta dot equals to omega. Circular motion with constant angular speed, right? So the option will be a uniform circular motion. Yes, that is the correct option. A spiral expanding trajectory, no. A damped oscillation is not. A decaying spiral is not. So a uniform circular motion. Okay. How we can tell this? We have seen that theta r dot equals to 0. So obviously r is constant. Otherwise r dot is not equals to 0. Theta dot equals to omega, and theta dot is the angular speed. And it is a constant angular speed because omega is a constant right now. That's why. Okay. Now coming to the 17th question. For x dot equals to 2xy plus y cube, y dot equals to 2xy plus x cube. The system is a gradient system and does not permit limit cycle, is not a gradient system, permits a stable limit cycle, is conservative. Okay. First of all, to have a gradient system or not, what is the condition for that? Let me write here the equation first. Plus y cube. Y dot is 2xy plus x cube. Yes. So, if del x dot del y del y dot del x. Then it is a gradient system. And also, if del x dot del y equals to del y dot del x, then it described, it can be described by a single potential function. So our question was there. What was the question? Yeah, so the question was like, the system is a gradient system or not. So to have the gradient system, as I told, that del x dot del y should be equals to del y dot del x. Now coming to this question. For this question, x dot is 2xy plus y cube, y dot is 2xy plus x cube. So first calculate del x dot del y. So it is 2x plus 3y square. Del y dot del x is 2y plus 3x square. Now simply we can see that del x dot del y is not equals to del y dot del x. So the system is not gradient, right? Okay, system is not gradient. Very good. So obviously I can go here, the second option. Okay, so maybe we can go for the 18th question. The system x dot equals to x into 1 minus y square, y dot equals to x into 1 minus x square. This is a conservative, admits a stable limit cycle, is a gradient system, has chaotic solution. So just previously we mentioned that what is the condition for a gradient system, that del x dot del y is equals to del y dot del x, then it is a gradient system. So we will first check that whether it is gradient system or not. X dot equals to x into 1 minus y square. X into 1 minus y square. Y dot equals to y into 1 minus x square. Just a minute. So del x dot del y. Del y of x into 1 minus y square. This will give me the answer as minus 2xy. Now coming to del y dot del x. Del x of y into 1 minus x square. So this will give me minus 2xy. So we can see that del x dot del y is equals to del y dot del x. So obviously we can say that this is a gradient system, right? This is a gradient system. Okay, fine. And it can be described by a single potential function. And one more thing is that such systems has no stable limit cycles. This is to be noted. Okay, now coming to question number 19. The dimension of a strange and attractor is. Okay. The dimension of a strange attractor is what? Integer, infinite, fractal, 1. Okay, so a strange and attractor, let's say like Lagrange or Rosler, this has fractal dimension. What does this indicate? It indicates that it lies between integer dimensions. And for more information, it has self-similar geometry and sensitive dependence on initial conditions or values. So what does this mean? A strange attractor has a fractal dimension and it lies between the integer dimensions, obviously, and it also has the self-similar geometry and sensitive dependence on initial conditions. Like these strange attractor is basically very much sensitive on the initial conditions, initial values. If the initial condition or value are getting changed, then the strange attractor behavior will also be changed, and it has a fractal dimension. So this one will be the correct one. Okay. Now coming to the last question. The dimension of a chaotic attractor is usually. First of all, that one was the strange attractor. And what about the chaotic attractors? Chaotic attractors are typically fractional dimensional. Okay, it is basically reflecting complex non-integer dynamics in phase space. And for more information, this property of chaotic attractor distinguishes them from the regular periodic orbits. So regular means I will talk about that integer dimensional. Okay. So the chaotic attractors are typically functional, fractional, dimensional. It is basically reflecting the complex non-integer dynamics in phase space. And this property, that fractional dimensional property of chaotic attractor, distinguishes them from the regular periodic orbits. So this is again the fractional or fractal. Okay. So the dimension of a chaotic attractor is usually fractional, which is fractal, like obviously non-integer. And for integer one, it is the regular periodic orbit, but for the chaotic attractor, it should be fractional or fractal, dimensional. Okay. So I think this comes us to the last question. Yes. So for this case, we have already finished 20 questions, and I will just a little bit go through these questions again for the better understanding. And as this is the last week, so yeah, we will stop this session by just going through all the questions quickly. Okay, Lorentz equations cannot describe the motion of a classical particle because the phase space dimension is even. Yes. The van der Pol oscillator cannot describe a Hamiltonian system because it involves nonlinear damping with the x dot, right? That is x squared term is there in x dot. So nonlinearity is present where? It is present in the damping one. Which of the following statements is true about a limit cycle? A limit cycle is a distinct closed trajectory in phase space. Okay. A limit cycle in a nonlinear dynamical system is best described as a closed trajectory in phase space that is stable under small perturbations. Okay. In 2D phase space, if the coefficient matrix has distinct eigenvalues, the eigenvectors will be linearly independent to each other. If the Jacobian matrix, means the coefficient matrix of a 2D system, has complex conjugate eigenvalues with negative real powers, the fixed point is stable spiral. And Sir has already given the example of this stable spiral, like why we are telling that that eigenvalues which has a negative real part basically leads to the fixed point of stable spiral. Sir has already given the example of these things, so I don't want to go through there, but just the thing is that if the Jacobian matrix of a 2D system has complex conjugate eigenvalues with real parts, the fixed point will be the stable spiral. A chaotic motion is aperiodic as well as it will be a deterministic. It is not a random one. It is deterministic, and it is basically depends on the initial conditions. A system that exhibits sensitive dependence on initial conditions but evolves deterministically is said to be chaotic. For the system x dot equals to y, y dot equals to x minus y, the fixed point at origin is unstable spiral. Yes? Okay. So we have just seen that one, like x dot equals to y, y dot equals to x minus y. So for these cases, we are having a negative, like lambda 1 and lambda 2 are real, but one is positive, another one is negative. It is showing that unstable spiral. So the answer will be unstable spiral. Now coming to the question number 10. For a system x dot equals to y, y dot equals to minus x minus y, the origin represents stable spiral. Okay, how? Because we have seen that for x dot equals to y, y dot equals to minus x minus y, the coefficient matrix is such that the eigenvalues are complex, as well as there will be a real part which is negative. So we can see that the lambda 1 and lambda 2 are like minus half plus root 3i by 2 minus half minus root 3i by 2. So obviously we can see that minus half is there, which is giving me the negative eigenvalue. I mean negative real part. So this is indicating stable spiral, decaying oscillation. Okay, for the system x dot equals to x, y dot equals to minus x, which of the following is true? Here the coefficient matrix we just need to construct. The coefficient matrix is 1 0 minus 1 0. So here we can see that the trace of A equals to 1 and the determinant of A equals to 0. Yes. Now coming to question number 12. It is showing that x dot equals to y, y dot equals to minus x. Then again, what is the condition of A, like trace of A or determinant of A, what will be the value of for this? And we got that trace of A is 0 and determinant of A is 1. How? We can see that x dot equals to y, y dot equals to minus x. So A is 0, 1 minus 1, 0. So we can see that the trace of A is 0 plus 0 is 1. 0. Then determinant is this. Question, like option this. Okay. Then question number 13, for x dot equals to x minus y, y dot equals to x plus y, the eigenvalues of A are. So the A matrix is 1 minus 1, 1 plus 1. So yes, this is the A matrix, and the eigenvalues corresponding to 1 minus 1, 1, 1 is like lambda, like the characteristic equation is lambda square minus 2 lambda plus 2 equals to 0. So lambda is 1 plus minus I. So lambda 1 is 1 minus I, lambda 2 is 1 plus I. So the option is 1. Okay. Now coming to question number 14. For x dot equals to y, y dot equals to minus x plus y, the eigenvalues of the system matrix are. So the coefficient matrix is coming out as 0, 1, minus 1, 1. So for this case, I am having the lambda values as 1 plus root 3i by 2, 1 minus root 3i by 2. Okay. So the answer is 1, 1. Like the first one, 1 plus root 3i by 2, 1 minus root 3i by 2. Then coming to the 15th question. For x dot equals to x minus y, y dot equals to x plus y in polar coordinates, the equation is what? R dot equals to r, theta dot equals to 1. So how it is coming? Basically what we have done here, the polar coordinate, like x dot equals to x minus y, y dot equals to x plus y. So x equals to r cos theta, y equals to r sin theta. So x dot is x minus y, y dot equals to x plus y. So we are just putting that x, we have calculated first x dot y dot in terms of r dot theta, r dot theta dot. Then we just put that one in x dot equals to x minus y, y dot equals to x plus y equations. And we are getting these expressions that, okay, like after simplifying a little bit, we are getting the values of r dot and theta dot. And we are getting the answer is like r dot equals to r, theta dot equals to 1. Okay, yes, this one. Now question number 16. In polar coordinates, if a system is described by r dot equals to 0 and theta dot equals to omega, then the motion is a uniform circular motion. So circular means how it is coming as circular, because r dot equals to 0, which is giving me r equals to constant. So it is a circular motion, like the radius is constant for a circle, right? The circular motion. But how it is uniform? Because theta dot equals to omega, where the theta dot is the angular speed, and angular speed is constant. So theta dot equals to omega, so it comes out as a uniform circular motion. So I have just explained these things clearly. If r dot equals to 0, theta dot equals to omega, the radius of the motion of the particle stays constant always, r equals to constant, that's why. And theta dot equals to omega means angle increases uniformly. This represents uniform circular motion with constant angular speed. Actually, okay, fine. Now coming to question number 17. For x dot equals to xy plus y cube, y dot equals to 2xy plus x cube, the system is not a gradient system. Why? The condition for having a gradient system is that del x dot del y should be equals to del y dot del x. So if we just do the partial derivative with respect to y in x dot, the partial derivative with respect to x in y dot, then we are having that del x dot del y is 2x plus 3y square and del y dot del x is 2y plus 3x square. Both are not equal, so the system is not a gradient. Okay. Now coming to question number 18, the system is a gradient system or not. For that, we have calculated that del x dot del y and del y dot del x are equals to exactly equal, which has the value minus 2xy, I think. Yes. So obviously this is gradient system. And it can be described by a single potential function. These systems have no stable limit cycles. Now coming to question number 19. The system of a strange attractor is fractal. Sorry, the dimension of a strange attractor is fractal. It is not an integer dimension, right? Why? A strange attractor like Lorentz or Rosler has fractal dimension. It lies between the integer dimensions. It has self-similar geometry and sensitive, very much sensitive, dependence on the initial conditions or values. Now, the dimension of a chaotic attractor is usually again the fractional or fractal. Why? Chaotic attractors are typically fractional dimensional. It is reflecting the complex non-integer dynamics in phase space. This property of chaotic attractor basically distinguishes them from regular periodic orbits. And regular means like obviously the integer dimensional. So the answer will be fractional or fractal. Okay, so these were the questions for week 12 assignments, previous year assignment. And with this, I just want to conclude classical mechanics of a single particle NPTEL course live interactions. Thank you so much for all of your efforts and all of your advices. I'm really grateful to have this course, and I'm really grateful to have as a TA, which is teaching assistant for this course under Supratim Mukherjee, Professor Supratim Mukherjee. And yeah, thank you so much and have a very good day and all the very best for your final exam of classical mechanics of a single particle. And I hope all the participants, all the registration people will do a very good job on this exam. And yeah, so not only for this exam, wish you a very all the best or best of luck for all the exams in your coming future in your life. So if you have any doubt, anything, you can just mail me in that mail ID what I have already shared, or you can just contact with me through NPTEL coordinator, that is also fine. And I think you people will have the admit card very soon, because the exam is going to happen very near. So all the things are there, and yeah, all the very best. I hope that the exam will be totally very good for everyone. So yes, and obviously I think I have already mentioned in the previous class that the exam will be computer based, and there will be MCQ type, MSQ type, and numerical questions as well. These things I have already mentioned in the like previous class. If you did not attend the class, then you can just go through the YouTube videos and you can have this information there. And obviously I think I have the information about this question like about the pattern of these questions in the last class PPTs as well, so you can go through this one as well. And I think this is in Google Drive. Okay, so anything else? I think there is nothing, but obviously I'm telling so many times for this week at least this is a little bit advanced topic, so we don't need to, like, you people don't need to bother about this advanced topic in this course at least. Like, if you want to know more about this classical mechanics of a single particle or nonlinear systems, nonlinear dynamics, then you obviously go through these pages, like you obviously go through these topics very carefully. But for this course exam perspective, I can tell that it is not that much important, like the week 12 at least. Okay, but obviously other weeks are very much important. And I can also tell you that the assignment questions were really important, super important. So you have to take care about these previous year assignment as well as this year assignment questions, uh, because that will help you too much in the final exam. I think I have already mentioned that one in the previous class as well, because the assignment gives a very confidence that okay, we can do better in our final exam. And final exam, I can tell you, almost 40 to 60% is coming very nearly as the assignment questions. So you can understand that a huge number, a junk number of questions are coming, like obviously not exactly the same questions are coming, but very similar questions are coming in the final exam. So that's why I'm telling that the previous year as well as this year uh, assignment questions are super important for the final exam. So just go through these previous, like the current year assignments, total 12 weeks, as well as the previous year questions. Like previous year questions you did not have in the question like format, but I have already discussed that one in our classes. So you can just go through these things, that will be very much helpful for you. And anything else? I think that's up to today. And all the very best. And I am again telling that I am not taking any extra classes for this course, classical mechanics of a single particle, as it is more than enough for this course, that like 12 week, and then each and every week are 2 hours course. So that's why I'm not taking an extra class. And obviously if you have any doubt, you can just ask in the discussion forum portal. There I and the professor will also be there, available there. So obviously we can have the discussion there as well. Yeah, so yes, do this. Okay, so now bye bye.